In recent days, science news outlets have been buzzing with claims that signs of life may have been found in space. This time, the celestial body at the center of attention is a distant exoplanet called K2-18b, located 124 light years, roughly 1.2 quadrillion kilometers, away from Earth. A team led by Professor Dr. Niku Madhusudhan from the University of Cambridge reported detecting a molecule known as dimethyl sulfide, DMS, in the planet's atmosphere, a substance that, on Earth, is produced almost exclusively by living organisms. Unsurprisingly, this announcement sparked enormous excitement. Headlines quickly proclaimed that one of the strongest pieces of evidence for extraterrestrial life ever discovered might finally be in our hands. However, when we carefully examine the science behind these claims, the situation turns out to be far more nuanced. Not only is the connection between dimethyl sulfide and life on an exoplanet highly debatable, but even the certainty that the detected signal truly belongs to dimethyl sulfide is not as solid as it was initially presented. The story begins with the Kepler Space Telescope, named after the great astronomer Johannes Kepler and launched into space in May 2009. Kepler's primary mission was to search for Earth-like planets orbiting stars beyond our Sun. Using its photometer, Kepler observed approximately 530,506 stars over a span of 9.5 years until it ran out of fuel on October 30th, 2018. From this enormous dataset, scientists identified 2,778 confirmed exoplanets. Even today, Kepler's data continue to be analyzed, meaning this number may still increase. When we include discoveries made by missions that followed Kepler, we now know of at least 5,876 exoplanets. This is no longer a speculative idea from 30 or 40 years ago, wondering whether planets like ours might exist elsewhere. We know they exist, we can observe them, and perhaps some of them host intelligent life forms who, through their own telescopes, can see Earth, but remain uncertain whether life exists here. It is a genuinely mind-bending thought. As part of this broader search, another exoplanet was discovered in 2015, K2-18b. Its seemingly dull name comes from the standardized system used to label exoplanets. K2-18 refers to the host star discovered during Kepler's second mission phase, while the letter B indicates the first planet found orbiting that star. In systems with only one star, the star itself is often referred to without the A designation. The K2 label signifies Kepler's second mission, initiated after a malfunction in its reaction wheels forced a revised operational strategy. We already know quite a lot about K2-18b. For instance, it lies within the so-called Goldilocks zone, the region around a star where temperatures could allow liquid water to exist. The exact boundaries of this zone depends largely on a star's brightness. Brighter stars have habitable zones farther out, while dimmer stars require planets to orbit much closer. K2-18b orbits its star at a distance of just 22 million kilometers, compared to Earth's 150 million kilometers from the Sun. However, its host star emits only about 2% of the Sun's brightness. As a result, its habitable zone spans roughly from 18 to 46 million kilometers, placing K2-18b squarely within it. This means that, at least in principle, liquid water could exist there. But how could we possibly know what exists on a planet so unimaginably distant? The answer lies in spectroscopy rather than direct imaging. Even with our most powerful telescopes, we cannot directly resolve such small, distant worlds. To see something as small as the flag left on the moon would theoretically require a telescope with a mirror hundreds of meters wide, far larger than anything we can currently build. Instead, astronomers rely on indirect methods. One of the most ingenious is the transit method. Rather than observing the planet itself, we monitor the brightness of its host star. If a planet passes directly between the star and Earth, it blocks a tiny fraction of the star's light, causing a brief and measurable dip in brightness. From the depth and frequency of these dips, scientists can determine the planet's size, orbital period, and distance from its star. For K2-18b, these measurements reveal a planet with a radius about 2.6 times that of Earth and a mass approximately 8.6 times greater. This information alone already tells us something crucial. Its average density is roughly half that of Earth's, making it unlikely to be a rocky, Earth-like planet. But the transit method offers even more. As starlight passes through the thin edge of a planet's atmosphere during transit, certain gases are absorbed by specific wavelengths. By analyzing which wavelengths are missing, scientists can identify the atmospheric composition. This is how we detect molecules such as hydrogen, methane, carbon dioxide, and potentially dimethyl sulfide. When the James Webb Space Telescope observed K2-18b, it confirmed the presence of methane and carbon dioxide. These are relatively common gases. The intriguing outlier was dimethyl sulfide. On Earth, this molecule is produced almost exclusively by living organisms such as phytoplankton and bacteria. Moreover, dimethyl sulfide is usually difficult to detect because its signal is often masked by other hydrocarbons. To be observable from such a distance, it would need to be produced in quantities millions of times greater than on Earth. This is where the excitement originated. If dimethyl sulfide is truly present in such abundance, what could be producing it? However, several major issues undermine the claim that this is evidence of life. First, the statistical certainty of the detection is not strong enough by the standards of physics. The reported confidence level ranges from 95% to 99.7%, corresponding to about 3 sigma. In physics, truly robust discoveries typically require a 5 sigma confidence level, over 99.9999%. Some independent analyses even suggest the signal may be as weak as 1 sigma, meaning it could be statistical noise rather than a real detection. Second, the nature of K2-18b itself poses problems. For dimethyl sulfide to be produced biologically, the planet would likely need to be a rocky super-Earth or a hypothetical ocean-covered Hycean world. Yet the planet's low density strongly suggests it is neither. Instead, the data are most consistent with K2-18b being a mini Neptune, a small gas-rich planet with no solid surface. If K2-18b were covered in vast oceans, we would expect to see large amounts of water vapor in its atmosphere. Instead, the atmosphere appears dominated by methane, with little evidence for water vapor, ammonia, or other key biosignatures. This significantly weakens the biological interpretation. Moreover, while dimethyl sulfide on Earth is associated with life, it has been detected in non-biological environments, such as comets and interstellar gas clouds, places where life almost certainly does not exist. This suggests abiotic processes, possibly driven by photochemistry or stellar radiation, can also produce this molecule. K2-18b orbits its star extremely close to its star and is likely tidally locked, always presenting the same face to its sun. Combined with the intense magnetic activity of red dwarf stars, these conditions could radically alter the planet's chemistry and enable exotic non-biological pathways for dimethyl sulfide production. In short, while the discovery is intriguing, it does not constitute evidence for extraterrestrial life. The media's enthusiastic headlines greatly exaggerated the strength of the findings, often without fully engaging with the underlying science. In this particular case, even the researchers' public statements were sometimes contradictory, contributing to confusion and hype. The reality is simpler and more sobering. We have not detected life beyond Earth, but the search continues, and if life exists elsewhere, one day, through careful science rather than sensational headlines, we may finally find it. Until then, we keep looking.